So now that we've talked about these different memory technologies, let's move on and talking about an introduction to caches and why we have caches and where this really comes from sort of first principles perspective. And to start off motivating caches, let's draw the most basic memory system we can draw. So in our abstract computer model, we have a processor, and it connects to somewhere to store our data and our instructions, or our main memory. And the time it takes to actually access something like our main memory can many times be much, much larger than our cycle time, or the latency can be much, much larger. So that DRAM I passed around, to get a byte out of, or to get like the first byte out of something like a modern day's DRAM, it's going to be thousands of instructions. Or probably around, it's probably right around 1,000 actually in a modern day computer. It's gotten a little bit better, as we'll see on the next graph, for a funny reason. But and the bandwidth we're going to define as the sort of number of accesses per unit time. So as I said, for the close-in arrays, you can usually access them much faster and have more bandwidth through them, sort of by definition. But for things far away, you have to have less bandwidth, kind of by definition, because you have to probably go through some pins or some buses that have to go very far away. And then we're going to define the bandwidth delay product as the amount of data that can be in flight at the same time. And as you have sort of things farther away and more bandwidth, this bandwidth delay product gets bigger, because you're multiplying sort of the amount of stuff, the amount of bandwidth you have times where everything can be in the pipe. And you basically have a big pipeline of sort of thousands of values in flight. So this is what I was alluding to about the gap happening between DRAM bandwidth and processor performance. So memory technology has been sort of slowly getting faster, and processor technology got a lot faster. The one thing that's at least not so bad anymore for single scale or for single processor performance, we've sort of flattened out at this point. So now RAM is getting faster. Unfortunately, this is still keep going exponentially here if you sort of look at multi-core. If you have multiple cores in the same chip, the amount of aggregate processor performance is going up relative to the memory performance, and things get worse. So here we have a 4-issue 2 gigahertz superscalar accessing 100 nanosecond memory. DRAM can execute 800 instructions during the time to access that one memory reference. And we have things faster than 2 gigahertz now, and we also have slower memories than depending what memory system you put in, it can somewhere roughly about 1,000 instructions. Okay, so what's an important first order effect when we're looking at memory systems? Well, size does matter. As you have larger and larger memory systems, it just takes a longer time. There's more capacitance you have to drive, and you have to go physically farther. And you can't fundamentally fight the speed of light. It's going to take you a certain amount of time to go a certain distance. And if that distance is farther, it's going to take you longer. So you also have sort of more fan out if you have bigger memory systems. So our physical size is important here when we're thinking about memory systems. OK, so let's now introduce a cache, or an idea of why a cache is good. So let's look at a notion of memory hierarchy. Unlike this picture where we had a processor connected to all of memory in the system, we're now going to put some intermediary levels. So we have a processor, and we're going to put small, fast memories here. And we're hopefully going to try to access these small and fast memories instead of accessing this big, slow DRAM. Let's look at the capacity here. The registers, so your general purpose registers or registers that hold, let's say, your program counter specialized registers in your processor, has very small capacity. SRAM has more capacity. DRAM has even more capacity. And it's sort of double less thans there to accentuate that you can fit a lot more in the same space. though the latency follows that same hierarchy there. An important other thing to think about when you're building memory hierarchies is that on-chip memory bandwidth is typically a lot higher than off-chip memory bandwidth. If you're on-chip, you can run wires there, but the second you have to go off-chip, you have to go out the pins of the chip, you're going to be limited. And what this really boils down to is the pins or balls or solder columns. So modern day chips, we don't actually have pins on them anymore. Instead, we have ball grid array, what is little tiny solder balls. The size of those, the pitch of those, is still much larger than the wire on chip. A wire on chip is so much smaller than the solder ball, which is, or in modern day, actually, like something like your x86 Core i5 or something like that, or Intel Core i5, actually has what's called land grid array, where you have a little array of little they're pads, little metal pads on the bottom of the chip, and then there's these little pins that are actually located in the socket on little, they call them pogo sticks, but they're basically little pieces of metal on springs. And you put the chip in, and then the little pogo stick hits the piece of metal, and that's the contact. On older chips, you actually had the pins on there, on the chip itself, and you sort of put it into a big socket. And in the middle is ball grid array. But anyway, all those things, the connection technology to get off the chip is much larger. So you can fit fewer of them in the same area than if you were to wire on chip. And that's really this insight here that on-chip bandwidth is a lot larger than off-chip bandwidth. And because of this, you're going to want to think about putting small, fast memories close by on chip, where you can store data. OK, so what happens in this memory hierarchy? When we go to access data, if the data is in our fast memory here, we're going to go here, hit in our low latency SRAM will say, and come back. If the data is not in the fast memory, we have to go all the way out to our DRAM and come back. And memory hierarchies work only if you're going to find useful data here. So if you go build a small, fast memory close by, but you never find any information in there that you need, why did you build this structure? You're just sort of doing extra work and burning extra power. And this is one of the key insights of why we have caches, or what a cache is that when we go to build a memory hierarchy like this and we introduce something like a cache, by finding the data nearby that's going to be faster to access, we need to find the data there with high probability. Otherwise, we should have just not built it and just gone out to main memory all the time. We were just wasting everyone's time and area and cost. So memory hierarchies only work if you have your fast memory actually is useful. OK, so let's look at different memory access patterns and try to come up with a couple different techniques that we can exploit to increase the probability that the data we're going to need is in that small, fast memory. So we have an interesting graph here. I want to explain what this is. And we're going to look at a toy example first, and then we're going to look at a memory trace, memory reference trace from a real operating system with a real program running under it. But let's start off with some examples here. We have time on the horizontal axis, and we have address on the vertical axis. And it's something like your machine, let's say it has 4 GB of RAM. We actually have sort of a line across here for every single address in the machine. And then we have time. And as the program executes and goes and accesses different pieces of memory, we're going to put a dot on this graph. So let's start off by looking at something like an instruction fetch. Typically, programs will execute in order. They'll execute the first instruction, then the next instruction, and the third instruction at the addresses, sort of monotonically increasing, unless you hit a branch. So let's take a look at some instruction fetches. We start off by executing some code. And then we're going to actually execute a loop here. So when we're in the loop, we're going to be executing the same piece of code over and over again. And if you look at that from an address perspective, we start off not in the loop. So we have some address here, some different address. And we execute these 3 addresses, Then we execute those 3 addresses again, those 3 addresses again, those 3 addresses again. We keep fetching those 3 addresses over and over again from our memory system. And at some point, we exit the loop and go execute something else. OK, there's a pattern there. Now, we're going to think about whether we can exploit that pattern in a second. Next, let's talk about accessing the stack. So computer programs typically have stacks. This is where you either spill or fill registers for. Typically, you also use it to pass arguments. And you spill and fill. Most modern-day compilers will do that when you make a function call or return from a function call. And the argument passing is around function calls also. You'll put arguments that the later functions need on the stack, and then you go execute that. Alternatively, you can store the arguments in registers. But in something like x86, we'll say you're going to put arguments onto the stack. And you also put local variables onto the stack, because it gives you a convenient place to put it. So let's take a look at what happens when you go to do a subroutine call. When a subroutine call, the stack is at one address. The stack pointer is somewhere here. And when you go do a subroutine call, you're going to push all of your registers onto the stack. So you're going to put something here, put something here, put something here, put something here, and the stack pointer is going to logically increase. And then once you're in the function that you called, you're going to want to access the arguments. And those are usually very close together. They're all right next to each other on the stack. Or you might have to go access the argument over and over again. This is if you don't have enough registers. Like in our first lecture, we looked at a stack-based architecture. And a stack-based architecture, we had to actually push onto our stack the same value multiple times. It's pretty common to reuse the same local variable or reuse the same argument because you don't have enough registers. And you want to go load that data from your stack over and over again. So it's pretty common to access very close together on the stack, maybe probably the same within a cache line, or access the data very close by. And then when you're done, you return from the subroutine, and you're going to pop all the data off the stack. So time is increasing this way, so you're going to remove in reverse order. OK, let's look at some data accesses. The one I wanted to focus on here is actually vector accesses. So what's a vector access? Well, this is something like an array. And arrays, a lot of times you'll be reading the first word or the first byte, then read the next byte, and then you read the next byte, and you're doing some operation across all of it. So let's say we're taking a matrix addition. We have one matrix, and we're adding it to another matrix. And they're single-dimensional matrices. You're actually going to be reading different addresses, but they're going to be in some pattern, and they're going to be sort of close by. Now, if you're accessing, let's say, every 4th element in an array, this distance here would get larger. The address distance is going to get larger, and your access patterns are going to get a little bit farther apart. And scalar values, these are sort of singleton values. So a good example here is, let's say this array that we're doing here is we're trying to take an array. Instead of add 2 arrays together, we're going to take one array, and we're going to add 5 to every single, or some variable x, which has, we'll say, 5 in it, to every single element of the array. So what your processor would do is it would first load the thing you're going to be adding to, so the data from the matrix, and then load from the scalar value x from main memory. Do the add and do a store. Then you're going to load to the next location of the vector, load the x, do the add, put it back, and continue that on. OK, so can we try to exploit different types of locality? And this slide is really important to grasp what's going on in caches. And this is probably the most important slide in today's lecture, is to grasp what's going on here with the different patterns we're seeing, and how do we exploit these patterns. OK, so there's 2 types of patterns I want to talk about. And your standard cache system is going to exploit these 2 patterns. But let's first of all look at them individually. And we'll be able to see the patterns here. First one we're going to talk about is temporal locality. Temporal locality is this notion that if you access a piece of data, you're likely to access that piece of data again in the not too distant future. So it might be useful to keep that data nearby. So temporal locality, I'll say again, is if a location is referenced, it is likely to be referenced again in a short period of time. So let's try to identify that in these diagrams so far. OK, well, I see that a few places. These argument axes, we access some value, and we're going to go access that value again pretty soon, then again pretty soon, then again pretty soon, and again pretty soon. And we're basically accessing something with high temporal locality. Likewise, these scalar values here, the scalar axis, we're accessing again and again and again. It's this exact same address, and the time between one axis and the next axis is pretty close by. OK, now let's look at this and see, are there other interesting access patterns here? Well, interestingly, on a stack, when we go to access a value, and we're pushing our values onto the stack, it's very common to access a value at, say, address 1,000, and then go access 1,000 plus 4, 1,000 plus 8, 1,000 plus 12, 1,000 plus 16, and access all of the nearby values. So what are we going to call that? Is that a common pattern? Well, yeah, it's pretty common. And we see that here. We see it in loops for instructions. We're actually accessing one instruction. It's very common for us to go access later instructions very close by, packed, let's say, next to it. This is pretty common that you just fall through in your code. So we're going to define this and call this spatial locality. And spatial locality says if a location is referenced, it is likely that locations nearby it are going to be referenced in the near future. And these are both just heuristics. There's nothing magical about these. These are just heuristics of how programs happen to work out. But we're going to build systems that try to leverage these two heuristics, or these two characteristics, rather, these two types of locality to improve the performance of our processors, or be able to use those small little RAMs that we're going to put in our memory hierarchy and actually store useful data in them. I also wanted to sort of point out that you can have both spatial and temporal locality mixed together. So if we look at something like running a program which has lots of loops, we have spatial locality because we're executing instructions nearby, but we also have temporal locality here because we're reusing all of this data again and again and again in a short period of time. So in the near future, we are accessing sort of the same data over and over again. Even though it's not the exact same piece of data, it's nearby. So we're sort of seeing both spatial and temporal locality exhibited there. OK, so let's look finally at a real memory reference pattern or real memory reference trace. And this has the same axes of what we saw before. We have time, and there's one dot per axis. And then we have memory addresses. I don't know what the unit on the vertical is. It's probably not. It's probably in like thousands or millions or something like that. And this is from a study that some people at IBM did many years ago. But we're going to look at this and see different patterns show up here. So the first thing I want to circle here is spatial locality. So we see that along this line here, we access the first piece of data at, let's say, this address. And we then go on and access all of the data subsequently. So this is as if we were like reading an array. We just read all the values in the array. So we have spatial locality that because we went and accessed element 1 in the array, there's a high probability that we're going to go access other data values which are nearby in that array in a nearby time. Let's take a look at temporal locality. So horizontal lines here are temporal locality. And we can see that this program is accessing this value over and over again, or at least values very close by. It's hard to tell on this resolution. But this is temporal locality, that we're accessing the same values or most of the same values over and over and over again. And then finally, we can see both temporal and spatial locality in these little blocks here. We can see that we're accessing similar sorts of addresses, which is going to be spatial locality. And we're doing it all within a short period of time. So we're seeing temporal locality of reference. And caches can exploit both of these. Caches are going to exploit temporal locality by keeping data that gets used and reused many, many times nearby. So when you see accesses which are temporally close by, or temporally spaced, so in time are spaced nearby, what's going to happen is a cache is going to sit somewhere here before you get to a main memory system. And when you go to access a value, it's going to memorize that and keep that value nearby. So if you go to access it again in time, and if your program exhibits temporal locality, that data value will be close by, and you won't have to go out to the big, slow RAM. And caches can exploit spatial locality. And the way caches go about exploiting spatial locality is that when you go to access a particular piece of data, your cache is going to pull in data around that piece of data. And we'll talk more about this next time, how that works. But we're going to segment data into what we call cache blocks or cache lines. And that's typically those cache blocks or cache lines are aligned. And when you go to access a piece of data, it might be somewhere at the beginning or at the end, or it might be in the middle. You pull in all the data around that. And the heuristic here is that if you access some piece of data, let's say you only go access the first byte in a cache line, you're likely to go access other bytes in a block, so multiple pieces of data around that. So we're able to exploit spatial locality here.